Oh, thanks.
All right.
Okay.
Next, we have Yedi Zhang from the Gatsby unit, who's going to talk about training dynamics of in-context learning.
Thanks for the introduction and for organizing this beautiful workshop in this beautiful place. So I'm Yedi Zhang. We're talking about training dynamics of in-context learning and linear attention, and joint work with my three wonderful co-authors in the little circles, Aditya Singh, Andrew Sachs, and Peter Latham at University College London. And we'll actually present it again exactly next week at ICML 2025 as a spotlight, in case you're also going. A one-sentence summary of our work is that we characterize analytically the training dynamics of multi-head linear self-attention trained for this in-context linear regression task. So first of all, why is the training dynamics of attention models important? It's probably increasingly important and relevant because in the large language model era, people typically do not train their models to convergence anymore. Then you really care about the training dynamics, not just the converged model, because we rarely get to the converged model. And what's more, it has been found that the in-context learning abilities of attention models, or just abilities of attention models in general, evolve with training time in very interesting and non-trivial ways. So in this very influential blog by Anthropic in 2022, they found that the in-context learning ability of attention usually emerge abruptly at some time point during training. And more recently, people have found that in-context learning have algorithmic phases during training, and people didn't have a theoretical explanation for why these things happen, and we're going to see both of these two features, abrupt and algorithmic phases, in our setup. All right, so that's training dynamics. And then why do we care about the training dynamics of linear attention? So linear attention is the regular softmax attention, but without the, the regular attention, but just without the softmax renormalization operation. It's more analytically tractable, and it captures many important optimization properties of the regular attention. And there's literally a paper called Linear Attention is brackets, maybe all you need, to understand transformer optimization. And I also just want to highlight that linear attention, despite its name, is a nonlinear model. Because if you just look at this expression, it's nonlinear in the weights, and it's also nonlinear in the inputs. So we're not trying to use a linear model to capture the behaviors of a nonlinear model. We're trying to use a nonlinear model to capture the behaviors of another nonlinear model. So it maybe seems more believable to you when people say that it does capture many of the behaviors of softmax attention. All right, so this is our model, and the task we train our model on is called in-context linear regression. It's a canonical instantiation of in-context learning, and I have here a screenshot of me prompting ChatGPT to do the in-context linear regression task. So I have a string of numbers, 112, 325, 176, and 48 question mark, and I ask it to fill in this question mark. And you probably have noticed that I generate these numbers according to a linear map, which is like I add the first two numbers to get the third number. So the question mark number should be 4 plus 8 should be 12, and ChatGPT does correctly output 12. So this is one input-output prompt, and you can do this again with a different linear map. So in the second prompt, I used a different linear map, which is I subtract the second number from the first number. So then the missing number in the question mark should be 3 minus 1, gives you 2, and ChatGPT again correctly outputs 2. So this is the in-context linear regression task, and we call the first 3 rows of the input the context, and the last row is the query. And if we write things with letters instead of numbers like a proper theorist, the input to this model is always a matrix, and we're writing things in the same way. So the first n rows is the context. It has like n pairs of small x and small y's, and the last row is the query, and I generate the small y's in context according to a linear map of the small x. And the target output is like what the model should fill in this 0 here, which is the same linear map applied to the query token xq. And the important thing here is that the W for each input sequence is different. So in the first sample, the W is 1, 1, because I'm adding 2 numbers. And in the second sample, it's 1 minus 1, because it's subtracting 2 numbers. It's different every time. If it's the fixed W, then it's linear regression. But it's a new W every time, so it's in-context linear regression. What the model needs to do is to do linear regression on the blue numbers in context to recover that W, and then use that to predict the query output YQ. And in practice, in the simulations and computation, we sample our linear maps W from standard Gaussian, and I sample my small x tokens from a zero-mean Gaussian distribution with covariance capital lambda. And I'm just going to give you the spoiler of tell you just what the linear attention model is going to converge to. So what it converges to is that YQ hat is going to converge to actually approximately least square linear regression in contact, which is somewhere of 1 n from 1 to n, yn, xn transpose. And then this is the xy correlation in context, and then in inverted covariance matrix, and then times x cubed. So this is approximately least square linear regression solution in context, and you can write that alongside my definition for the attention model, which is x is skip connection plus sum on all my hats, 1 to h, wv, my value weight, times x transpose, key weight, query weight, another x. And we notice that there is an xq in capital X, and there is also exactly a sum on n from 1 to n, yn xn, in this matrix. There is a block in this matrix that's exactly that. So what is left to be learned is just the inverted covariance matrix. So the value, the key, and the query weights, they just need to learn the inverted covariance matrix. And they will also just make use of the useful things in useful blocks in the XX transpose and X properly being able to implement this model. All right, so now that we have established that what we need to learn is just the inverted covariance matrix, let's see how it learns that with respect to time. So we first start from linear attention with rank 1 key and query. So usually we have multi-hat attention with low rank key and query matrices, and the rank of the key and query matrices, these two matrices is a hyperparameter. We're going to start from the rank 1 case and then proceed to the more general low rank case. And we train our model with square laws with gradient descent from small initialization. So we're in a rich feature learning regime. And these are the loss curves of linear attention with rank 1 key and query. The multiple curves are just different random seeds. And what we consistently see is that the loss go through the plateau and then it suddenly drops, and then another plateau, another sudden drop. And we find that's actually saddle to saddle training dynamics. Each time it plateaus is because the weights are going near a saddle point on the loss landscape. And we calculated the amount of each of these transitions and find they are approximately eigenvalues of this covariance matrix. So the first drop is approximately the largest eigenvalue. The second drop is second largest eigenvalue, and it goes on. And there are 4 drops in total because my small x here is actually 4-dimensional, so there are 4 eigenvalues to be learned. And simultaneously, what's happening inside the model is that if you plot the weights in different attention hats, actually key or query weights in the different attention hats, what it is doing is that at the first abrupt transition, the loss decreases by approximately lambda 1, and the key or the query weights in one of the attention hat is going to grow from the small initialization and align with the first eigenvector. And then in the second drop, it drops by approximately lambda 2, learns the second eigenvector, and it goes on. And we are able to reduce each of these transitions, each of these abrupt learning, to a one-dimensional ordinary differential equation about just one scalar value weight parameter, which is given by this differential equation, and we'll plot the solution of that as dash curves, and the simulations as solid curves, and they do agree very well. All right, so with that understanding, we're able to characterize or identify what kind of in-context learning algorithm the model implements at different time points during training. So say if you stop training, or early stop training during right after first abrupt loss drop during the second plateau, what you get is a model that does principal component regression in context with just one principal components. And if you stop at the right after this 2 abrupt loss drops, it implements principal component regression with 2 principal components, 3 principal components, 4 principal components. When it has learned all the principal components, it's just linear regression, least square linear regression. Because the first step is like learning actually number one, inverse E1, E1 transpose. These are eigenvalues, these are eigenvectors. And then in the second step, it learns number two, E2, E2 transpose. And it learns all the eigenvectors, which gives you, recovers this entire inverted covariance matrix. So it's like consistent to the common folklore or intuition that attention models develop increasingly sophisticated in-context learning abilities during gradient design training, except that in this case, we theoretically characterize exactly what increasingly sophisticated means. It means principal component regression in context with increasing number of principal components. All right, so this is the picture with linear attention with rank 1 key inquiry, and I promise that we're going to the general linear attention with rank R key inquiry case. And the picture is pretty similar to the rank 1 case, except that now learning occurs in chunks of size R. So the far left figure, it's like rank 1 key inquiry. It learns one eigenvector at a time, so the loss drops number 1, and then number 2, and then goes on. If you have a linear attention with rank 2 key inquiry, it learns 2 eigenvectors at a time, so the loss drops by number 1 plus number 2, plateaus, and then number 3 plus number 4, and then plateaus. And the similar things happens for the rank 4 and rank 8 cases where like learning occurs in chunks of size 4 and chunks of size 8. And the behaviors are like quite clean here. And also you might have noticed that there are like tiny plateaus here as well. So there is a big plateau every time you learn a new attention hat. And there are like these tiny plateaus every time you learn a new rank in an existing attention hat. All right, so that's everything I have for linear attention today, and we have also some simulations with softmax attention. It's the same task, same model, but just with the softmax renormalization added onto the model, and it does do something similar. It also has multiple abrupt loss drops, and during which they're like learning one eigenvector at a time. All right, so that's pretty much it. To summarize, we study the training dynamics of linear attention trained on an in-context linear regression task. We find saddle-to-saddle training dynamics, and we simplify reduce each of these transitions to a one-dimensional ordinary differential equation, and we identify the in-context learning algorithm at different time points during training, which is principal component regression in context. And with that, we make a theoretical case for the progressive improvements of in-context learning of attention models during gradient descent training. And I have said like approximately many times in the talk, like approximately least square linear regression in context, approximately drops by an eigenvalue. We do make those things more precise in the paper. And there is also more on like why we have and how we arrive at these results. So it's there in the paper. And thank you for your attention.
Very nice. I see lots of hands coming up. I'll go like this and I'll start with Mason.
Hi, thank you for the talk. I'm curious about if you take this linear attention model and just start adding layers to it. It seems like the kind of essential simplification might be preserved when you do that because it's still a polynomial essentially, and you still have some simplicity relative to the softmax thing. So I'm curious if you've what happens if you've looked at what happens when you do that, and if you run into a showstopper, or if there's just you might be able to extend those methods more in that direction.
Yeah, thank you for the question and advice. I think that's a very good future direction, but we didn't look at that. So I'm not quite sure what will happen. So you can view the one-layer linear attention model here as it can implement cubic functions of your input. And if you have second 2 layers, and then it's polynomials up to the 6th order, and then the 9th, and then the 12th, and then you're able to do more complicated things with higher order polynomials. It is indeed an interesting direction. We're not sure yet what happens there.
Hi, really nice talk.
Thank you.
So one question I had is, even just in the rank 1 case, so you have these 8 different attention heads. So I don't know if you looked at the dynamics or if your results get to this, but is it the case that one attention head picks up each different eigenvector, or are they learned in these different stages, but different attention sets are capturing like different combinations of eigenvectors. Does that
The
make
first
sense?
case.
It's the first case. So
Yeah.
you actually have, so like, I see. So at the beginning of training, wouldn't it be that all the attention heads try to go to the first eigenvector?
They do, but only the one attention head with like the luckiest or the largest initialization is going to be faster than all the other heads, and it's going to learn the first eigenvector.
Okay. And then the other ones like start moving.
Yeah, I think that the other case does happen in, say, like linear networks or other nonlinear networks. But for attention, it actually is indeed, like actually, so here, this plot is like one row is one key weights in one of the attention heads. So I have 4 heads here. So I'm plotting, say, for in this case, the key weights right after the first abrupt loss drop. And you can see only the first head has learned the first eigenvalues. And all the other 3 heads are basically white, which means they're near 0.
I see. Okay. That's very clean. Cool.
Thank you.
Yeah, thanks again for the talk. I had a quick question. So in the higher rank case, is there anything interesting that happens with the factorization that you get across the keys and queries? Or does it do sort of the naive factorization in the training dynamics? The product is lambda inverse, I guess, right? So
what factorization would be considered naive?
I don't know, E transpose, I guess. And there's like, I don't know. Yeah, is there anything interesting about the factorization?
I think it does similarly to the rank 1 case. So when you have, say, rank 2 key and query, your WK and WQ is, I think, and then you have K1, K2, then Q1, Q2. So one attention head just basically does like the sum on 2. I don't know why I write summation for 2 things. So it's just Q1, a Q1 transpose, K2, Q2 transpose. So when it's rank 2, it's just like adding to, it's adding to vector outer products. And I think it's going to learn like E1, E1, E2, E2 again.
Oh, I see. That's what happens. Okay, that's.
Yeah.
Okay, perfect. Thank you very much.
Thank you.
Ian.